for two different periods. You see that, and you see the standard deviation ratios, standard deviation runoff over precipitation. Here you see, well, two plots, but I do not discuss that in the moment. And the model, the era versus the GCM, our system lies just in between them. We have other standard deviations. Here you have the correlation between evaporation and precipitation in the theoretical curve, and you find that scatter plot for GCM and era. There are two different colors in here. And likewise the correlation between runoff and evaporation. This is how we did it. If you look at hydrologists, they look in individual watersheds. Understand for that. But I'm not looking at that area.
At what scales are these model?
A grid point scale. Grid point scale.
And in time as well.
Annual values. Annual values.
Annual values.
Annual means I'm in climate. I should have said that before. I'm in climate. I'm not short term. No storage is involved. It is steady state.
Okay.
The system is steady state. I'm not looking on your scale.
Yeah.
Okay. I'm not doing that.
And
I'm not doing that.
Yeah, sure. But grid points mean what? 100 kilometers? Or the mesh size?
Wait. For the analysis for the attribution, the NDVI has a high resolution. We scale them up to era scale.
And it is
era
should be
50 something. 50 something.
Yeah. Okay.
Kilometers, not meters.
No, sure.
So that is the scale. Basically, the equations come from watershed scale. You know, the first derivations is watershed scale. This is
well, first, there's a very good news, because what you presented looked like the kind of solution of what we are supposed to do now for the IMA project about Tibet Plateau.
Yes,
you did almost everything.
We don't need to tell anyone, you know.
Yeah, not to say that.
No. There are further things which could be done with that. Higher resolution and other lakes. The interesting thing is, I like to test my lake model because the lakes are expanding in Tibet, and then what happens?
Okay.
Why is that the case? And the biome relationship with the D relationship, it was for our point of view very important to see whether NDVI, which is the measure of forest, etc., you know, the greenness it is, how well is that represented in the Buddhical sense, and was it not so good?
Another thing is a little bit different but connected to the rest is what you presented first, the stories about the well-known paper, I don't remember, about the records, the
record rainfall, yeah, 1950 Jennings.
Yeah.
Yes.
But the funny thing, we had a paper with Pierre Hubert which derives this law just based on multifractals.
Yes, I know.
So it's a bit different, the approach.
That it is different. It is different.
Yeah.
On the end, it might not be very different because the intermittent part within AR process, the sense of AR, is very funny.
Yeah.
I do not understand it theoretically. I wanted to derive it theoretically, you know, but I'm missing to find someone who does the mathematics better than I can. Because what appears, I forgot when we did the job, you know, if you look at the sense of AR, whether the intermittency comes in, if you just say the sense of AR also represents a binary. What does the binary spectrum of the sense of AR show? Okay, does it also show the one of AR? And that is what I was interested in when you were talking about the binary values of your contamination changes.
I will find that also.
Okay, thanks.
I have another question about your last part, because
the risk.
Yeah, because you said there are many people are working and people are so different areas of research. So I suppose anyone should say that their research is the most important to improve resilience. So how you were
You mean that risk stuff?
Yeah, yeah.
Yeah.
Oh.
So what were the parameters, indicators, if you want to evaluate that resilience was improved? Because, for example, economists are mainly saying, okay, we will have less losses.
Along the horizontal axis.
Another one will, yeah, okay, but it's very often contradictory to, for example, ecologists, because they're saying, okay, you're taking the most economical model, but it decreases the resilience of ecology and so on. So how to put all of that together, not anyone will be satisfied.
Well, first we did not want to satisfy everybody because we are working on global aspects.
Yeah,
Global. And ecologists are generally working on smaller scales. Maybe global to biodiversity. Well, with us, biodiversity fits into Cassandra here. All right? You have the biodiversity problem, you have climate change problem. They're all very similar, for politicians to discuss that. Because your aspect is one underneath. Because once we see biodiversity, blah, 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 fits in there, then the politics, we require from politics what could be done. They should improve the predictability here. And you only can improve by more research on, and then people can discuss what they like.
Yeah, but how do you prove that the money which were invested by politicians in doing that it's indeed doing something?
Okay, we do not have an example for that.
So you did not develop any type of the indicators that could be...
As scientists, what we did is gave the administration or the government a way how to look at it, and then experts should go on and see how that could be implemented. It is not, we are not we're finding that an interesting subject for policy advice, and in particular in global changes.
By the way, there were no specialists about policies in the group. No? Among co-authors, you said there are 3 economists, but there were nobody.
No
political science.
No, political science. This is a bit policy. He's a sociologist, and no, this maybe that is not half bad. Oh no, this one. Wait a second. Klemmer, he was the boss of the one of the big economic institutes advising the government. Should go to. But this is not a politician. No, this is a separate. Well, this consultation is to put it on a scientific background and not how to implement it.
Yeah.
Okay.
Yeah. Okay. No other question? Okay. Thank you very much. We have a second talk presented by Levent Kavvas, who is a distinguished professor at the University of California at Davis, which is nearby San Francisco, in fact. Nearby.
Good food and
depends on the traffic jam. Yeah. And he's a fellow of the American Society of Civil Engineering, and has been working in many different aspects of mathematical and physical modeling of hydrological fields, I would say. Yeah. Thank you. Okay. And you will present something which is doubly fractional. So
I'll bring something that's much different in scale.
Yeah. Okay.
Than what Klaus
So I will
present.
let you present your title.
My presentation is at a very different scale.
Compared to the one of Klaus, yeah.
Yeah.
Much smaller.
So Klaus is dealing with the whole world. I'll be dealing, with a very, very, very small part of that world.
A
So
few atoms,
transport
yeah.
processes. So
Yeah, well, I can say it's fractional ensemble average governing equation of transport by time, space, non-stationary, stochastic, fractional flow.
let's see why I said what I said. So, transport really is rather fundamental to almost all flow processes. Although we usually consider transport in the context of scalars, and that's the case that I'll be really dealing with. Actually, fundamentally, the whole fluid mechanics is about transport. That's what it really is. So I'll be actually looking at it from a rather basic perspective, because there has been all these in a way confusions, and people really in the United States get very aggressive, and they usually kind of can kill each other if they catch each other in a dark corner somewhere, because some are like as we are going to see, random walk guys, and then some of them are fractional differential guys, and these people when they get into one room, it gets very heated, the whole thing, and as if these are very different things, as we are going to see. Actually, they are not really different. They are just basically the pictures of the same reality. That's all they are. The whole issue really came about because we are dealing with these transport problems, and we need to be dealing with some models, some transport models for contaminants, and however in these processes we have been seeing behavior that really are not supported by the data, the observations, as has been performed by many different people, really do not support the standard view of transport, which fundamentally is in a nutshell the diffusions, what's called as the diffusions, the diffusion theory. So what I like to do is I like to actually start with that, because it's really important to understand where people are really coming from. The original, the theory of diffusions actually has been developed by the famous G.I. Taylor in 1922. He has a paper on diffusions, basically by random walks. He basically showed how you can model the contaminant spread in the Thames River, just to, basically came up with the first model, and then later on suggested an important modification in 1954, to that model upon the suggestion of Batchelor in 1949. In a nutshell, what is really happening is that one needs to be defining basically this phenomenon, as I'm going to show later on, as how one would be moving from, say, one increment to the next. Now, if you are thinking, in the standard framework, which Taylor did, later on Batchelor, and others who followed in all the way, to about 1980s, 1990s, the thinking was basically local, meaning, that you just interact. Basically, if you are starting at some location in here, you only can move, to this direction or to this direction. Interaction only among the immediate neighbors. This is really important. It doesn't matter, what dimension you are. Okay. So I'll be looking at it, in one dimension, in space, and one dimension in time. So under such a framework, Taylor basically was able to show that for the transport of a solid by time-space stationary stochastic advective velocity field V of xdt, where xdt is the Lagrangian location of a solid particle at time t in one dimension, then one can express the dispersion coefficient basically as half of the time rate of change of the variance of the displacement, which actually can be written in terms of the variance of the stationary velocity times an integral, a time integral of the autocorrelation function, basically, for the velocity. Now, this particular function being basically, dealing with a stationary velocity field, if you take it to t going to infinity, will give you a constant number. If you get a finite number, then, for this integral going to infinity, you are going to basically end up with a constant number for this derivative, which basically is what is called as the dispersion or the diffusion in statistical physics. That is the true definition of the dispersion. However, engineers completely ignored this whole theory. What they did, what they have been doing, my own colleagues, in my department, just use it, as a fitting parameter. They'll take, the diffusion equation, and then they'll use, that d as a fitting parameter. Yet, this whole definition and, the resulting equation really has huge implications. Because if you define, the problem in this context, then what follows is that the variance of the pollution particle displacement just becomes basically a linear function of time, with this slope basically equal, to that dispersion coefficient. This was all nice, but the business was good. This was United States, more or less, 1970s, 1980s. My predecessors, they were having a ball. They had, these million-dollar projects. They had great time. This is University of California. They looked at all these, pollution problems. You might have heard of people like Hugo Fischer and, Jerry Orloff. These were big names. I was the child of these guys, actually. And I was brought in, The good news is these guys actually told me, look, we hired you not to follow us, but to do something different, okay? Just do whatever you want, but you need to come up with something different. Maybe that's why they brought a strange guy like me into the system. Anyhow, that's really what happened. Now, just, in the late 1970s, 1980s, people started, coming up with some observations that were challenging, this theory. Because as we are going to see, this theory is basically a local theory, local interactions. And whereas, Nordin and his colleagues at USGS were looking at the whole transport process, basically the sediment transport process, and then some people in the groundwater field, Silliman, Levy, Erkowitz, these people were showing that this whole transport process was really not following this Fichtean idea. In other words, the variance of these particle displacements were not linearly varying with time. They were basically showing that that's not the case. So the issue suddenly became, okay, if that's not the case, what to do. And in the starting about late 1990s and early 2000s, two particular approaches gained popularity in United States. One approach is this approach of the random walks, what's called as the continuous time random walks, and the other approach is and has been the fractional transport equations, the fractional advection dispersion equation. Mainly developed at the University of Nevada at Reno by a mathematician, Mershard and Baumer. These were mathematicians, and then their colleagues, Benson, basically their students, Reno Schumer, Jung, and others. And they have been still, putting out a lot of papers on this thing because, using this fractional advection dispersion equation, they were able to show, that you can actually end up with this non-Fichtean, behavior in transport. You can get, these long tails in time and in space. Basically, they were able to simulate, the Levy motions and all these things, using these fractional, differential equations. This sort of approach was also, applied in the surface waters, the transport in surface waters. In fact, I myself, we tried to, use some, again, basically develop some theory for the non-Fichtean, dispersion. So what was the problem with all this thing? Well, the problem was this fractional advection dispersion equation basically, in a way, was like an empirical equation. All they did is they just took the usual diffusion advection dispersion equation, and then instead of the integer derivatives, they basically started using fractional derivatives. Whereas the advective velocity, the dispersion coefficient, these were taken still as integers, and furthermore basically taken as some constants. And then they were philosophizing. There are maybe more than 100 papers now on this stuff, looking at, okay, what if this happens, that happens, or whatnot. But of course, there are always some other groups which have different interests. So Berkowitz et al., who were pushing for the random walk approach, basically criticized these fractional differential equation guys, saying, well, basically said that this fractional advection dispersion equation places the mechanism of non-Fichtean behavior entirely on the fractional powers of space and time derivatives in the equation. They also questioned, the model's ability to account for the evolution to a Fichtean regime, basically meaning that, okay, you guys are doing, all this fractional stuff, but you are not really obtaining, the situation, where you actually have diffusions, because in nature you do have diffusions. You can also have the transport, solid transport, taking place in a very diffusive manner, besides having these long jumps that you can have. Now, as an alternative, they proposed a model which was actually developed by physicists Klafter and Silvey in 1980s, what's called as the continuous time random walk model. Then, of course, there are others. Shlomo Neumann, if you have ever heard of this guy, he's like the Pope of hydrology. So he and his student Tartakovsky criticized everybody else. They said,
that's usual.
right, because he's the Pope. You see, he can say whatever he wants. So he basically said, none of you guys are doing the right thing.
Exactly.
So they basically said, that there's a lack of a theoretical framework that would lead, to the fractional, advection dispersion equation, and questioned, the meaning of the fractional parameters, in this fractional advection dispersion equation. However, I must admit, that they were actually right, because there was no derivation, real derivation, of the fractional advection dispersion equation. They did not really start from the basics to derive, these equations. I'm talking about the fractional advection dispersion equation that these guys were using. I'll get to that. Now, because, you know, I mean, they were using, for instance, you know, these integer parameters, there was no justification as to why they were doing, you know, what they were doing. Meanwhile, again, Shlomo Neumann and Daniel Tartakovsky, these guys questioned the flow field stationarity and the no correlation assumption underlying this continuous time random walk. The problem, you know, with this continuous time random walk, again, as we are going to see, is the following. Now, in the case of the diffusions, the usual standard, you know, diffusion models, as I said, you can only, you know, make these transitions among the immediate neighbors. Now, what they were observing, you know, in the field is you could actually see, you know, these displacements from any location to any location. So you could see, you know, these very large jumps. They were, you know, seeing, especially during the disaster times. Well, you know, in fact, I was just watching the television, you know, the other day, like in southern France, you could see the transport of these cars. I mean, you could see, you know, these pile of cars. So something more than some, you know, regular diffusion is taking place. I mean, to throw these cars, you know, on top of each other. I mean, there's a, you know, the transport is somewhat different mechanism than the regular transport to be able to carry, you know, these substances or these scalars, if you like. Now, a similar story also is happening in time as well. You can also look at this problem, you know, for the diffusions. You again, you know, have just local interactions in time as well. So that when you are looking at a, you know, standard, you know, diffusion equation, you basically also, you know, are only looking at, you know, these local interactions, you know, in particle displacements. Now, what the continuous time random walk people, like, you know, in that paper by Klafter and Silbey, they actually are considering only the stationary sort of transport. What that means is that the transitions that are taking place are independent of the time-space locations from which, you know, these displacements start. Now, the problem is, in nature, when you look at, you know, for instance, a groundwater aquifer, you will clearly see different sort of formations. You may see, for instance, you know, like volcanic formations. You may see sedimentary formations. You may see like clay layers. You can see, you know, limestones. So you will see, you know, these different layers, obviously, you know, randomly placed, you know, in this medium, so that basically the displacements that are taking place are actually very much dependent upon the, you know, those locations, the spatial locations. So the transport itself is really not just homogeneous. You are not dealing with a homogeneous medium. So these transitions, as the way, you know, they were formulated in this continuous time random walk, are not just universal. They will change, you know, with space and time location. They do. I mean, you know, the other guys basically opposing, you know, these continuous time random walk guys, you know, have shown, you know, given some examples. So basically, then the issue becomes this. All right. So no derivation, you know, general derivation, you know, for these fractional advection dispersion equations. And then, you know, the question is, are these two models really different or not? I mean, are they the same thing or are they different? What's going on? So in this, you know, presentation, I'll be basically talking about the generalized time-space non-stationary random walk model for solid transport by non-stationary stochastic flow, and then, you know, the fractional random walk model by non-stationary stochastic flow in fractional time-space, and then from these one can also obtain, you know, the fractional differential equations for transport. So we are going to see that, you know, and then probably the most importantly, we are going to look at, you know, some simulations to see, you know, how these different models, you know, actually perform, you know, against, you know, the Monte Carlo solutions, you know, of the problem. There's a lot of mathematics in here. I'm going to basically just go directly, you know, into this particular expression in here to basically describe, you know, what's happening. The fundamental situation, the setting really is given in here for any given time increment, say, you know, t to t plus delta t, when the particle is doing a displacement, it can actually, in general, it can do any sort of displacement. It can either, you know, just move to its next neighbor, or here, or where, everywhere. And then, you know, the interaction can be from everywhere to everywhere. This, in fact, you know, is not only in transport. We are seeing, you know, these teleconnections. I usually watch what's going on, you know, in Eastern Europe, where my heritage comes from, you know, against, you know, what's going on in California. Very similar, you know, patterns I see, you know, talking about, you know, the climate similarities. There's a lot of similarities going on, so that there are these, you know, very long, you know, interactions going on. So you can actually model that. You can, in this context, what is really happening is the following. What we are seeing here is, this is the probability of being at the location x at time t, this one. This is the x at time t, the Lagrangian location, given that the transport started at x0 at time 0, and this is the displacement, okay, displacement during the time interval t to t plus delta t, given that we are at that location x sub t at time t. When you sum this over all displacements from minus infinity to plus infinity, then you will end up with the probability of being, you know, at the location x at time t plus delta t at this time, given that you started at x0 at time 0. So this is really the fundamental equation for non-stationary transport. Why? Because in this particular case, these displacement probabilities are dependent upon the particular space and time locations. Now moving on, again, you know, I'm not going to burden you with the details. I'll show you the reference later on for the detailed derivations. You can basically put this problem by taking y is equal to x of t plus delta t. You can write that particular equation in this form, and this equation actually is the generalized time-space non-stationary random walk model for transport by time-space non-stationary stochastic flow. We are going to see that in more detail, you know, in a few minutes. So the issue is, these are displacement probabilities. Can you actually write them down in terms of ensemble average contaminant concentrations? The answer is yes. For initial solid mass of unity, the solid particle displacement probable density is equivalent to the ensemble average solid concentration at time, space, location, zeta t. That is the ensemble average contaminant concentration C at spatial location zeta at time t, given that the transport started at x0 at time 0, is equal to the probability of that displacement from x0 at time 0 to zeta at time t. Now, using, you know, this particular equivalence, then and then also the generalized Taylor series for, say, you know, some function f of x around z. This is the fractional expansion for a function f around z. It is in Odibat and Shafave. In fact, there are some earlier papers, but this is the one that's being referred to. You basically will end up, with this fractional expansion. Now, in this fractional expansion, these derivatives that we see here, these fractional derivatives, are going to be Caputo derivatives. Why? Because I will not go, into the detail of the actual Caputo derivative. You can read it, for instance, in Pavlovny, this particular reference, Pavlovny book, which is a very nice book, by the way, on fractional calculus. Either there or in Odibat and Shafavne. These are Jordanian mathematicians, by the way, these guys. The reason why one needs to use the Caputo derivative rather than the Riemann-Liouville, the standard Riemann-Liouville derivative, in fractional calculus, is because when you are solving real-life problems, you will end up, with some integer derivatives as the initial conditions or the boundary conditions. Whereas, if you are using the Riemann-Liouville derivatives, then, you will have this problem of needing to come up, with this fractional fluxes for the boundary and the initial conditions, which may not be realizable. Okay? So, Caputo derivative has this very important, practical value. The results will not really change that much, by the way, if you were to use, the Riemann-Liouville fractional derivatives. Now, what you can do then, you can take, this particular equation in here and expand this equation in terms of the fractional expansion around y at time t. Okay, just expand, this equation around y, and at time t, around y and t, and then you are going to end up with this following equation, which is going to be the non-stationary random walk in fractional time space. Please note now that you have basically a non-local time, situation along with that non-local spatial situation. So you have basically an infinite number of fractional derivatives of all orders. All these are fractional, by the way, where alpha and beta are going to be between 0 and 1. So basically then, you can do the probability operation to end up with this non-stationary fractional time space in terms of fractional displacement moments. You can see now that you have these fractional displacement moments. Now, this is somewhat tricky because these fractional displacements can be negative or positive. Okay, so it's important because you need to follow these things so that you don't end up with these imaginary numbers. Okay, so this is basically what's going on in here. So we do follow up, between x of t and x of t plus delta t. So in this particular slide, I'm just describing that for k less than 0, x of t plus delta t is less than x of t, and the solid particle displacement k delta x, which is x of t plus delta t minus x of t, is negative. Then this will be the direction opposite to the main direction of the motion. Similarly, for k greater than 0, x of t plus delta t being greater than x of t, then the solid displacement k delta x will be positive and will be in the main direction of motion. So we end up, with this particular representation for the fractional random walk, by non-stationary flows. This is really important here. Why are we talking about that? Because, you can see that these particular displacement moments, these fractional displacement moments, are dependent upon zeta t, the location, where, the displacement starts. But these are all fractional, fractional moments. So, and beta basically is between 0 and 1. Okay, so we have such a model, then what is the problem? Well, people like Berkowitz, those guys, you know, the continuous time random walk guys, they were only dealing, you know, with the integer case, but because they have all these transition probabilities, you can basically fit just about anything you want, you know, with those transition probabilities. So they were able to, you know, look at power laws, they were able, you know, they looked at the Levy motions and all those things by just arranging, you know, those displacement probabilities. They were able to, of course, you know, replicate or simulate, you know, all these different motions to claim, you know, that their model is very general. As mentioned earlier, the problem, you know, with that approach is it's not really dependent on the origin of the motion. You know, these displacement motions need to be also dependent upon the particular location of the motion. Because, you know, the particular, whether, you know, you are in a clay layer or whether you are in a sandy formation, for instance, make a huge difference. It's also, you know, makes a difference, you know, whether you are, you know, in, say, you know, in the headwaters of a watershed versus, you know, you are in the main river. So the location is important. Time-wise, you know, you also have, you know, you need to be also considering the time. So why did they neglect it? Because when you neglect that, then, you know, you have just one single transition probability density, you know, as function of time and space lag. You can define it, so you have defined the whole process. Okay, I'll move on then fast. So that's the problem, you know, with this thing. Now, in this particular case, in this general case, however, you know, you have all these fractional moments. So the model has infinite number of parameters, if you like, okay? So it's not really possible to use it in practice. What you need to do is you need to specialize this into some special forms. So that's where, you know, these, say, you know, the convective transport model or the advective transport model really come from. You know, by specializing, for instance, you know, this particular expression for alpha power on the left-hand side and beta power on the right-hand side, then we will end up with the basically the purely advective form of the fractional ensemble average transport equation. All we do is just approximate the previous equation to just alpha order in time, beta order in space, performing this approximation, taking the limit as time increments go to 0, then introducing this equivalence between the probability density of displacement and the ensemble average concentration. One ends up with this following form for the pure advection form of the fractional ensemble average equation of transport. Now, what is really interesting, however, is in this particular form, those velocity terms, these advective velocity terms, actually come up with in these particular forms. In other words, for instance, V minus beta alpha is a scaled ensemble average advective flow velocity in the sense that it is the expected scale differential displacement per scale differential time. Only in the direction opposite to the main flow direction, and this is in the direction of the flow direction. In other words, this, you know, the scaling in time and space actually has a fundamental influence on the flow parameter. The velocity that one sees in these equations is not the usual, you know, my mother's, you know, velocity. I mean, these velocities are not integer velocities. They are actually fractional velocities that actually conform to the scaling, you know, that you take in time and space. That's what comes out. No assumption, no nothing in here. Moving on, if you just consider only, you know, one direction, of course, you end up, you know, just with this simple form, which is quite similar to the pure advective transport equation, you know, of the standard integer case. Now, moving on, if you want to obtain the advection dispersion form of the fractional ensemble average transport equation, then approximate the original fractional random walk equation to alpha order in time and 2 beta order in space to end up with this equation. as the moment form of the fractional equation, advection dispersion equation of transport. We have already defined, you know, these V terms. Now we have the D terms. Those are the fractional dispersion coefficient terms. Now they are defined, as you can see, in terms of the second fractional moments. Again, you know, when you look at the flow element, you know, displacement, if you like, they are, again, you know, functions of the particular time-space locations, and they are fractional. So, if you just look at the real-life situation of only, you know, upstream to downstream single flow direction, then one ends up, you know, with this following form for the fractional average ensemble average equation. It's interesting to see, you know, that you actually see the Stratonovich term appearing in this equation. If you are familiar, you know, with the Stratonovich differential equations, you know that there is going to be a correction term to the convective motion due to the dispersion, and that's basically what comes out in here in the fractional space. This term is a modification of the usual convection due to the effect of the dispersion. What is more interesting, however, is the cumulant form, because in 1954, G.I. Taylor basically said, look, you know, the more realistic form for these equations is not really the diffusion form, but it's the cumulant form. And the reason is because in the cumulant form, you can also conserve, you know, the covariance, you know, relationships, you know, the interrelationships in this context. So what you do is then, you know, in that fractional random walk, now you take 2 alpha order in time and 2 beta order in space, do the mathematics, and end up, you know, with this form when alpha is different than beta. Now, in the real life situation of one direction, then, you know, this whole equation, you know, just reduces to this form. What is really most interesting, however, is when alpha is equal to beta, and I'm going to explain that later on. When alpha is equal to beta, then you end up, you know, with some forms that are very close in representation to the integer form. Now you end up, you know, with these variances of the dx to the alpha with respect to dt to the alpha terms for the cumulant forms, alpha between 0 and 1, and in the mostly encounter just one directional flow case, then the whole thing reduces to this form. Now, in those equations, the variance, basically, you know, this variance minus is the variance of the fractional differential displacements per fractional differential time in the reverse direction to the main flow, whereas variance plus is the variance of the fractional displacement, differential displacement per fractional differential time in the main flow direction. So basically what we have seen is, you know, there is the case of when alpha is equal to beta, and there is the case when alpha is different from beta. What we did is then we ran some Monte Carlo simulations for this whole thing and evaluated, you know, the performance of these different forms. For the generation of the basically, you know, for the stochastic flow at vector velocity, we basically use our stochastic differential equation for the stationary case, which is forced, you know, by fractional Brownian motion increments, where A and B are constants in here. And for the non-stationary stochastic at vector flow velocity generation, we use this particular stochastic differential equation, where the diffusion term is modulated by a square root of time, still being forced, you know, by the fractional Brownian increments. Now, once you generate, you know, these velocities, once you obtain the displacements, then you can use, you know, the velocity definitions to obtain, you know, the velocities. Then you stick them in to these equations. Why two equations? Because your velocity can be either, you know, in the direction of the main flow, or it can be, you know, in the opposite direction. If it is in the direction of the main flow, then you use, you know, this equation. If it is in the opposite direction, you use this equation. That's why, you know, you basically have these equations. Okay, so we do the generation, you know, of basically after the generation of the flow field we use these equations to obtain the concentrations, and then we generate 500 of these realizations and then take their ensemble average to obtain the ensemble average forms. Now, then compare them against the theory. Against those equations 7, 11, and 17 for the purely advective form, for the moment form of the fractional advection dispersion, and for the cumulant form of the fractional advection dispersion. For different alpha values, we are considering a 1 kilometer span for the transport. Delta x is 10 meters. We have 100 increments. The time increments are 1 day. For the flow, the drift term is 1 meter per day. The diffusion term, however, depends on whether you have stationary, non-stationary, whether you want to have high variance versus low variance. And then we have generated 500 realizations by considering the following. We are taking basically just one increment, the 49th increment, and within that 49, in other words, from 490 meters to 500, and just putting a 500 milligrams per liter, concentration, solute concentration for the initial condition. And then, we do these generations for the flow velocity. We are looking at here for the fractional Brownian motion using this wavelet toolbox. You can read it. And then when we are in the Brownian motion case, when h is equal to 0.5, these are the cumulative motions where B is equal to 10 means you have high diffusion, meaning you have high variance in the flow field, but you are in the Brownian case, so you get basically, as you can see, the motion increments are highly varying. There's a lot of fluctuation going on versus when you take h equal to 0.7 and look at the motion increments, you get a much smoother correlated movement. Now, looking at this equation and considering the tails, you can see that as alpha basically decreases, the tail thickness actually increases. So you can control the tail behavior basically of these breakthrough curves by alpha, and that's what these fractional differential equation guys have done. Now, these three forms we have said. Now let us go into seeing how they compare against these Monte Carlo solutions. Now the black is the Monte Carlo solution of the problem. The light blue is the purely advective form. The red is the moment form, and the navy blue is the cumulant form. So when you are in basically you have a Brownian flow field with low variance and a stationary, you can see that the purely advective form and the cumulant form work very well when compared against the moment form. The moment form is more or less the usual standard form that people use. When alpha goes to 0.8, this is the situation. When alpha is equal to 1, this is the situation. Moving on, again you are in the Brownian domain, Brownian flow field, but now with high variance, stationary flow field. You can see that when the variance increases, no longer do you have a good performance from the pure advective form. This is the Monte Carlo, this is the cumulant form, this is the moment form of the advection dispersion equation. Alpha equal to 0.3, alpha equal to 0.8. You basically, again, have these. You can see the cumulant is doing the best. When you have alpha equal to 1, then the cumulant and the moment are performing very well. Moving to, again, to the Brownian case, low variance, but now you have a non-stationary field where the flow field is modulated by the square root of time. You can see, that the purely advective and the cumulant form are doing well for alpha 0.3, alpha 0.8. When alpha is equal to 1, however, you can see, that the cumulant and the moment forms are doing fine. Moving on, I'm just finishing, just 3 more slides. Again, the Brownian motion, high variance, but now you have a non-stationary flow field. You can see that the purely advective form is not doing well. Cumulant and the moment forms are doing much better. Here you have probably the most interesting case. Now you have a fractional Brownian motion flow field with low variance, stationary flow. You can see that the purely advective form is still doing well. Therefore, alpha 0.3, alpha 0.8. When you alpha is equal to 1, however, again, you see that for the low variance case, you can still see, that the purely advective form and the cumulant form are doing well. Finally, for 0.8, high variance, stationary flow field, these are the results that we end up with. Fractional Brownian field, low variance, non-stationary flow field, purely advective form, cumulant form, purely advective form, cumulant form. Here you can see that only the cumulant form is doing well. And finally, for this slide, you can see that the purely advective form is not doing well, whereas the cumulant and the moment forms are basically performing much better. In conclusion, is just for the results, if you look at these figures, you are going to see that the for the case, where this purely advective form is working, you need to have a flow field that's stationary with small variance and alpha power being less than 1. In the case when the solutions for the solutions of the moment form working well, for the cases of the Brownian motion and for the integer power. But in the majority of the cases where you can either have Brownian motion or fractional Brownian motion for the flow field, stationary or non-stationary, the cumulant form actually consistently works well. So, in conclusion, these fractional random walks and fractional differential equations are actually the equivalent models of the transfer process. They are no different. You can either use the one or the other. So these guys have no reason to fight each other. Actually, they are, except for ego, of course.
And for money.
And money, of course, because they need to get funded. Probably to me, personally, the most interesting thing that came out of this thing was this fractional advective velocity, flow velocity, and the fractional dispersion coefficients that emerge in these equations. They actually are reflecting the importance, the effect of the scaling in time and space on the flow and transport processes. And that is really the bottom line for this particular study. Thank you.
We have just a technical problem that we will be pushed out in 6 or 7 minutes.
I'm sorry, but it's a long story, as you can see.
So, yeah, it's a long story. Are there questions?
Yeah. Because indeed, from what you studied, it was close to me because I work with Moritz, and he, of course, has connection and with Newman and with Meyer-Schratt and so on. So that's exactly kind of bringing me back to all the question about main experiment. Because additive processes of type of Levy are nice and it's easy to put in the form, relatively easy to put of this fractional equation and so on, but there is only one problem, that when you are looking to the dispersion of the polytons, they are showing power law for extremes, but the slope of this power law is much larger than 2, so much larger than alpha, and that was the question that there is no real way to model it with just Levy stuff, except to create Levy and after that truncate everything which is too strong, which has no really theoretical reasoning behind it. So what do you think about it? Because in a given way that what I said yesterday, the model which is not finalized was created due to that, because it's only putting multifractal properties which could respect the power law with bigger value, could indeed solve this problem, at least in particular when there is really very strong pairs and so on.
Yeah, I mean, first of all, I did, in the paper, if you wanted to look at, the actual derivations, you can see the derivations in this particular paper, or the numerical, simulations, detailed simulations in this particular paper. First of all, these equations do revert, to the standard forms. In other words, from these equations, you do end up, with the standard, advection dispersion equations and, the convective equations when, alpha is equal to 1 and beta is equal to 1. Secondly, you just have any degrees of freedom. I mean, you have tremendous flexibility. I mean, you can take, if you use this fractional, random walks, you can take, any power you want. Because, you are looking at, basically an expansion, in terms of fractional powers. So you can cover, whole range of orders. In other words, just imagine, for alpha, like, if k is equal to 1, you end up with alpha.
But
then
we did not understand each other. I spoke about Levy flights, and in this case, indeed alpha is between 0 and 2, and we cannot produce power law which is high. So that's basically multifractals, multiplicative processes were created in order to be able to create power law with of the order 4, because basically for many atmospheres in the United States, the power law is much higher. So it's not the same alpha, okay, which I mentioned. So for me the problem is indeed that all these models which are based on the additive processes are not able to reproduce really extreme value of the pollution.
Well, what is interesting, however, is, there are two things that are going on. One is, the geometry, the other one is the dynamics. This is basically, taking whatever, is given, from the geometry. If you, from the geometry, give the appropriate, fractional powers, it's going to be reflected in the dynamics. That is the difference. Versus, just taking, just the fractals or just the fractional geometry and then running, the integer process. It doesn't make any sense to me. In any case, I mean, it's not a matter of, me, because, that's what the results came out. The results are saying, to me that, if you have fractional spaces, you cannot really use, just the integer dynamics.
No, that I agree, but for me, the question that in any case, the modeling of really dispersion coefficients and so on should include multifractal and not only fractal. And
the good news is it can. Because, all it's doing is, it's just giving you, a framework for, incorporating any alpha, beta powers, you want. Yes?
I have another question. I'm not sure the answer could be short, so in that case you
maybe
don't give
we can talk about it this afternoon.
Maybe later. Because once you put, in France we call it Langevin equation. In Japan, of course, they are speaking about Ito equation, differential equation of x with the noise and so on. And you put it only in the case of Brownian forcing.
Two
For
cases.
the other cases,
Brownian and fractional Brownian.
Yeah, only that. Are you always using Brownian forcing?
No.
No, I don't believe.
This is just purely, for the experiments, for validation, for sense, to see, how these models perform.
Okay.
The velocity field, actually coming back, to what you said, the velocity field needs to be determined by many factors. It is not necessarily, the fractional Brownian motion or Brownian motion. It could be anything. Just in here, we had to generate a flow field.
Someday we have to start and to go on discussing that. The good news is that you have a free lunch for those